All right. Thanks for the introduction, Pablo. So I want to take the time and for 10 minutes tell you something about MERTH. MERTH is an NSF-sponsored engineering research center. It's a consortium of 6 universities. Princeton is the lead. We have about 40 faculty, 100 plus students year-round, 140 students in the summer. And what the center is doing, it takes a technology that's just coming out of the research labs and tries to push it out into the real world. And to do that, it works very closely with industry. And the technology that we are pushing out into the real world is mid-infrared, laser-based trace gas sensing. So it's anything that's related with having a gas sample and wanting to know what chemicals are in there at very small quantities, parts per billion, parts per trillion sensitivity. So examples that come to mind: air pollution, urban air quality, indoor air quality, but also sensing for long-term air pollution. It is what amount of carbon is human-generated, which one is just natural carbon. Think about cap and trade, for example. So it's sensing of chemicals. It's also, if you switch from pollution and environmental to medical, it's breath analysis. If I breathe out, my breath has all kinds of chemicals in there. I can detect them. I can diagnose, monitor disease, and so on. It's also process control. It's automotive control. So it's sensing of chemicals. If you look at the sensor market, it's huge, right? There are plenty of sensors. But essentially, it falls into a couple categories. There are those that are cheap. That's your carbon monoxide sensor. It's cheap, easy to install. Everyone knows how to use it, but it's not sensitive enough. And then you have the other part of sensors that are wonderful sensors, sensitive enough, but they need a PhD to operate. They're expensive, they're bulky. You couldn't afford more than a few of them. So what's missing is a very high-end sensing technology, parts per billion technology, at a consumer product level. And we have a new technology. It's semiconductor-based spectroscopy. And being semiconductor-based, it should sit on the same curve as other semiconductor-based materials, on a Moore curve. The more you need, the cheaper they get. And so the ultimate goal is a small, tiny, cell phone-sized sensor that measures chemicals, vapors at very small quantities. Right. So we build little things, right? Sensors. How do we do that? It's an interdisciplinary, cross-disciplinary research effort where we combine the expertise of climate scientists. This is aerosols above Princeton on a sunny day. Medical expertise, breath analysis, with electrical engineering. This is a wireless module. It has all the electronics to run the system, detect the system on it. We talk about components. This is actually a gas sensing cell. It's about this tiny. And components, laser research. And why does it work? Well, if you think of trace gases, in the mid-infrared wavelength range, they have color. They have unique colors. And so if we can make lasers that match the colors of trace gases, we can detect them by absorption. So here's an example for ammonia. In the mid-infrared wavelength range, it has the strongest absorption lines, the strongest optical features. And so that's where we want to catch the trace gas and detect it. Just to make the point, different trace gases, they're all important ones. Each one looks different and very characteristic in that wavelength range. And so we have projects, 40 faculty, 100 plus students need a lot of projects to work on that are urban air quality sensing, regional climate, breath analysis, homeland security applications. It's sensor systems. It's point sensors, measuring a gas sample here and now. It is remote sensors, integrating over a couple hundred meters, integrating over a kilometer to match climate models, for example. It's sensor networks. Sensor networks is coming up very strongly. And then the little components that go into those systems that build the whole thing. Research. That was the research we are doing. A center such as ours has 2 more pillars. So it's the research, and then it has education and industry outreach. Here are education programs. They're more lively if you put pictures to it. But essentially, we graduate students who are better trained because they're more cross-disciplinary trained. They have visited more than just one university. Many of them take internships in industry. Many take international internships. So they're pretty much, they're very well versed in collaborating, in interacting with a variety of people when they graduate. And then, as Greg already mentioned, Greg Olson already mentioned, we work with industry. We have an active industry collaboration program where we provide membership at various different levels, where we provide services at various different levels, and we receive feedback, input, but also monetary cash contributions. And here's the list of our current members, and you see that it's small businesses, large businesses. 70% of our industry members are in fact small business and startup. And since our inception, Mirth in 2006, we have not lost a single company. We've only been growing in number of companies that we work with. All right, if I have 2-3 more minutes left, I thought I should tell you something about the technology we are doing. And we're doing a lot of things. So I pick one thing. And the one thing I picked is our field campaign last summer at the Olympic Games in Beijing, where we brought 2 instruments to do trace gas sensing and a group of environmental weather pollution forecasting modeling people. Right? So the pollution forecasting folks were part of the local team of scientists that provides feedback to the International Olympic Committee about pollution and the games. Right, so why did we go to Beijing, and why am I showing you this? First of all, it is to be part of something real. And so sometimes universities are accused of not being really part of the real world. I want to show you that we are part of the real world. We can get, especially engineers, we can get out there, our student groups, and be part of something where it matters. And Olympic Games do matter. So being part of something important. Next thing, it's a unique time series experiment in terms of civil and environmental engineering. That's extremely recent too. The question is, can a community influence on the short term its air quality? Right? Could New York City improve its air quality if it would put in congestion pricing? How do you do that experiment? That would be a very hard experiment to do. Here, we had a wonderful experiment because factories were shut down, car traffic was diminished to odd, even day driving, trucks, traffic was diminished. And the question is, can you actually clean up the air? And the answer is yes, it works really well. And finally, we wanted to test our equipment. And so we had actually 3 ammonia, carbon dioxide, and ozone that we were after, because you can measure them and they look very characteristic in the mid-infrared. And so we measured those trace gases with our experimental equipment. And the system's about this big. Well, it was an open path system where it sends out a laser beam 75 meters, beam comes back, and we measure along this beam path. It was about 2 miles from the main Olympic sites. We also compared it with the official instruments. And you go there and you see the official instruments, they're all from US companies, and there's a big box that measures ozone, and then there's a big box that measures ammonia, and there's a somewhat smaller box that measures CO2. And our box is about as big, but it can measure everything. All right, here's the example. This is ozone, day-night cycle, and our instruments does as well or better as the other instruments. All right. But just to show, we took out 10 students, some faculty, we all had fun, but we also were part of something important. And so, as a professor here, working with industry is another opportunity to be part of something real and something important. So we listen to you, what are important problems that need good solutions. And I think we're ready to help work on these things. Thank you.
Thank you.